record on the computer. We'll see if this works. Okay. So now with higher level, you're introduced to additional enthalpy reactions in here. And so in topic 15, you're introduced to energy cycles. And so energy cycles essentially, oh, what the heck? Sorry. I'm having trouble right now. Energy cycles, where you have different enthalpies that add up to equal the overall. So really it's just the Hess's law, but they like to put it in that term to kind of help you kind of see the movement between things. And so here you have a couple of different new enthalpies. So okay, enthalpy of hydration. Okay. Now, enthalpy of hydration is essentially the gaseous ion going to the aqueous, where the water is surrounding the gaseous molecule and dissolving it into the water. Okay. We have enthalpy of solution, which is your solid going into aqueous form. And we have lattice enthalpy, which is the solid going into gaseous ions. Okay. Now, these three enthalpies can actually form an energy cycle, meaning that they are all related to each other. And so what you can say is that if you want to solve for the enthalpy of solution of something, you can actually break it up into two parts. You can break it up into the lattice enthalpy, which breaks it up into gaseous ions. And then you can break it up into the hydration enthalpies of each ion. So again, it's called a cycle because it's just a different route to accomplish the same thing. And so if you add the lattice enthalpies and the hydrations of all the species involved together, you will get the enthalpy of solution. Okay. Questions about that? Okay. So that's an example of an energy cycle. So the enthalpy of solution is a sum of the lattice enthalpies and the enthalpy of hydrations. And notice the way I write it here is very important because the value of all these is based on this context of the reaction. So all your lattice enthalpies going from solid to gas, that's why all the values in your data booklet are positive, because you are going from solid to its gaseous ions. That's why that delta H is positive. Now, solution and hydration can be positive or negative depending on the ions. And that's all given to you in your data booklet as well. Okay. Huh? Oh, chat, sorry. Oh, no, I think that was Peter earlier. Yeah, okay. Oh, Maddie's here. Okay. So that's an example of an energy cycle. Now, the big one that y'all need to know is the Bohr cycle, okay? And it's just a more complicated energy cycle with 5 or 6 steps. Now, the good news is that it's still fairly intuitive in how you accomplish everything here, but you have to know a few new reactions. And so the reactions that I want to introduce you to are things like this, okay? Atomization, okay, is when you're going from a solid to a gas. I guess you could argue that sublimation technically as well, but atomization here is just the argument of converting a solid to a gas. Okay. You also have ionization, which you learn from topic 3 is essentially the gaseous metal ion losing an electron to become an ion. And that's the first ionization energy. The second one, I guess I should write this too. The second ionization energy is going from M plus gas to M2 plus gas and losing another electron. If needed, you would write that, okay? Bond enthalpy, like we said before, is taking a bond and breaking up the bond here, and those are both in gaseous state. Electron affinity. This is also from topic 3, is where you gain an electron to form a negative ion. And that's first electron affinity, and second electron affinity, if needed, would then be this, if necessary. And lattice enthalpy, going from this this. And I should also say that M and X are metals and nonmetals, respectively, but the charge on these examples, like for lattice enthalpy, is just generic. Like X could be a 2 minus, M could be a 2 plus. I'm just doing the most simple form of it, and we'll see kind of how that works. And what's crazy is that this whole cycle, when you illustrate it out correctly, ends up equaling the enthalpy of formation of that ionic compound, which is M solid plus, generally speaking, well, depending on what diatomic it is. I guess in this case, it'd be 1/2 X2 to make sure it's balanced, but it could be just X2 to accomplish that as well. So all those original reactions, when added up in the correct context, in the correct signs, equals your overall enthalpy of formation. And we're going to diagram it out so y'all can see. Oh, sorry. Since, let me move over here. Is that better? Okay. Questions on that? Questions on any of these reactions, I should say, because we're going to diagram it out in a second. You'll see when things become positive and when things become negative. Okay. And the way I wrote it in all these, this is the context and the value that you'll find in your data packet. So the way I wrote it here is the way the value will be presented in the data packet. So the way I wrote lattice enthalpy, the way I wrote electron affinity, that's the way this is the way the reaction is written in terms of the values in your data packet. So questions? Oh, did you get it written all down, Aiden? Okay. So what does this Bohr cycle look like? Okay, and I'm going to illustrate it this way, kind of starting from the bottom of it and illustrating upward, because I think it's important to kind of think about the energy changes in this. And so you're going to want to leave some space above you, maybe about half a page, so you can illustrate the rest of this here. So I'm going to start down here, and we'll do the most common one. Okay. So Na solid plus 1/2 Cl2 forms NaCl. Now, the only way to make NaCl is to make it from its ions. Like this. Okay. And what reaction, what type of enthalpy represents this change here? What enthalpy of reaction? Yes, Alejandro?
Lattice enthalpy.
Lattice enthalpy. Now, in this context, Alejandro, what sign should my lattice enthalpy, what should the sign of my lattice enthalpy be?
You should switch the sign
You
for
switch the sign. So it's negative whatever lattice enthalpy reads. Correct. And that's really important. And that's why I drew it this way, because I want you to visually see that it's exothermic. You're releasing heat. So it's the opposite direction. Okay. Now, you've got to figure out a way to get from Na solid and plus 1/2 Cl2 gas all the way to Na plus gas plus Cl minus gas. Okay. So we'll focus on Na first. Okay. What's the first thing we have to do to the Na solid? Atomization, right, Aiden? So this becomes Na gas plus 1/2 Cl2 gas. So that is atomization. Okay. Now that you have it in the gaseous form, what do you have to do to the Na gas now? Ionization, exactly. So this is ionization. And since sodium is just a 1+, you only have one value for it. It's just ionization energy of that one Na+. And keep in mind here that the coefficient for all these is 1, so the value that you're using is always going to be 1 of that, because it's per mole. Now Na+ is done. So what do we have to do to Cl2 first? Bond enthalpy. Now, the question is, Nathan, Aiden, why did I say Nathan? Sorry. Is if this is bond enthalpy, how much bond enthalpy have I done in this Bohr cycle? Like, what's my coefficient for this bond enthalpy going to be here? It's half, because you only broke half a mole of bonds because the coefficient is 1/2. So half a mole of Cl2 is being broken, so that's half a mole of bonds. So it's half the bond enthalpy, which makes 1 mole of Cl because you break it all up into 1 mole. Then after that, you have to convert this into this. Nope. Electron affinity, exactly. Okay. And that last arrow for electron affinity is kind of wonky, I know, because depending on which species like you have there, if it's like Cl or O, it might be positive, might be negative. So I kind of leave that one kind of ambiguous here, depending on situation. But this whole cycle, this plus this plus, oops, that's probably a bad color to use. This plus this plus this plus this plus this equals your enthalpy of formation. And the only one you really have to worry about sign-wise is your lattice enthalpy, because the lattice enthalpy is the only one that's reversed. So you could say in this scenario that enthalpy of your atomization plus your enthalpy of your ionization energy plus your enthalpy, or 1/2 your enthalpy of bond enthalpy plus your enthalpy of electron affinity, because now that you have 1 mole of Cl, then it is 1 mole of electron affinity, because the coefficient is 1 now. And then minus lattice enthalpy equals your enthalpy of formation. That's what that is. And so the coefficients matter because the coefficients will affect how you're multiplying your enthalpies, because every enthalpy you have is per mole. So if the coefficient's 1, then it's the same. But if the coefficient is 1/2 or the coefficient is 2, you have to do that to the reaction whenever you're changing something about it. Okay. Questions on that? Okay. So be careful about your coefficients as you're carrying them through, because, sorry, I'll give you all a chance to write this down. I know a lot of y'all are writing stuff down. Oh, sorry. Did I ignore this? Okay, there you go. Okay. Questions about this? Now that y'all have gotten a chance to write it down. Nothing? Okay. Along that same concept, we do talk about lattice enthalpy factors. So what affects the strength of a lattice enthalpy value? So looking at a formula here, I don't know if I have this here. I need to see if I can find it. I don't know if I have a screenshot of this. If I do, then I'll post it. If not, I'll have to go clip it. Oh, here it is. Okay. This is given to you in your data packet, lattice enthalpy. Now, also, if you notice, if you look really closely, the IB literally gives you the reaction equation for lattice enthalpy in the data packet. So like, there's no excuse for not knowing it, because it's literally printed in your data packet. And we'll spend time in probably March or February or April doing a get to know your data packet like lesson, where we annotate a data packet so you can kind of be aware of everything that's provided here. But when you look at these values here, okay, and let's say you just look at the alkali metals versus the halogens here, okay, they all have the same charges. They're all +1 and -1, okay? So what is the factor that really changes the lattice enthalpy values in this table right here? What affects it? What's the factor that determines why one lattice enthalpy is higher than the other if all the charges are the same?
Electron affinity.
No, not exactly. Not ionization energy. Just look at these values here, okay? So where's the biggest one?
LIF.
Okay, and where's the smallest one?
CSI.
Okay, Now, what's the difference? Oh, actually, even look at this, okay? Look at these values in the same column here. F is staying the same. What's changing about each of these species?
More electron shells. They're becoming larger.
Yeah, they're becoming larger. So one of the factors is ionic radius. The smaller, the greater the attraction. So if you're comparing, and this is a common thing they'll do on multiple choice, because in multiple choice, you don't have the data packet. So this is where they can ask you the question without you being able to use a data packet to get the answer, is they'll be like, here are 4 ionic compounds. Which one has the highest lattice enthalpy? So you'd look at the ionic radius if all the charges are the same. But you'll notice that more significantly, when the charges increase, it's more significant in the impact of it. So going from CaF2 to something like potassium KF, there's a huge jump in lattice enthalpy. So the factors are ionic radius and charge, but charge is the greatest one. You have to go? Yeah. That's fine. Okay. Just so you're aware now, Zoom, the last person that's in my actual classroom is leaving right now. So there's no one to bail you out when I ask questions now. So I'm just going to wait for y'all to answer. All right. Thanks, Aiden. Okay. So know that the charge of the ions and the ionic radius affect the size of the lattice enthalpy. But the charge of the ion first, that's your main effect. And if they're all the same, then you use the tiebreaker of ionic radius. So this is your tiebreaker, not your main factor. Questions? Okay. Now let's transition to something kind of completely, well, I wouldn't say completely different, but on to kind of different titles here, okay? And that is entropy and Gibbs free energy, okay? And so entropy, symbolized by S, is the distribution of energy among particles. Okay. Okay. Now, you'll probably hear that as the measurement of disorder. But it's hard to say, like, disorder, how do you measure disorder? So what you do is you say, okay, what are all the possible ways the energy can be distributed? And the more ways that it can be distributed, the more entropy there is, the more disorder there can be when there's more combinations of how the particles can be energized. So the higher the temperature, the higher entropy and things like that. And so if you're talking about it qualitatively, like just for kind of conceptual assigning a sign, we always talk about it in terms of delta S, okay? Because delta S is the change in entropy. No substance has an entropy of 0, because that would be absolute 0. Every entropy is positive, but the change in entropy can be negative or positive. And so things that involve a positive entropy change, okay? Going from a solid to a liquid to a gas. Phase changes in that direction create more disorder and more entropy. a temperature increase can create some increase in entropy. Solid being dissolved into aqueous, being dissolved in a solvent, that's an increase in entropy. And also, the moles of gas increasing. Because when you think about it, the only state of matter that really is significantly affected by entropy is gas. Because solids and liquids are fairly close together and are very restricted in their movement. Gases are much more free to move around. And so you'll see that the emphasis here is on the moles of gas increasing. And then conversely, everything in reverse is negative delta S. So if you see something like this, you're going from 2 moles of gas to 4 moles of gas. So that would be an increase in entropy. So that would be a positive sign for entropy. And it's only gas though. So when you're explaining your reasoning, you have to say the word gas moles, or you have to say moles of gas in your explanation. If you just say moles, you'll be wrong. They will take off because it's only the gas molecules that you're really counting in your equations or your balanced equations. Okay. Now, you can also actually calculate S, delta S from standard values. And you treat it like formation. So you treat it like an enthalpy of formation where it's products minus reactants. So you calculate all the entropy of the products and then minus reactants, which makes sense because if you think about it, you're measuring the change in entropy. So if your products have more entropy, then your sign should be positive. If your reactants have more entropy, then your sign is negative because you're decreasing in entropy. So again, it still at least makes sense when you're thinking about the values and what you expect the sign of the answer to be. The key thing that you want to remember, though, is delta S is in joules per mole Kelvin. And that's important that you understand that it's in joules because those units will come and haunt you later on when you're not calculating things correctly with delta G. Questions about that? Now let's go into Gibbs free energy. Okay. And Gibbs free energy is essentially the energy that can be obtained from a reaction due to delta H, delta S, and the temperature. Okay. And when you calculate this, if you have a negative delta G, or I guess delta G less than 0, that means you have free energy in the system, which makes it spontaneous, meaning that when this reaction starts, it will continue until it's all used up, because the reaction is actually producing energy that the reaction can use to keep it progressing and propagating forward. Okay. So spontaneous again means reaction can progress without additional influence. That means like you don't have to add any more energy and things like that to keep it going. Now, if your temperature is not one of the additional influences, like if it happens at a hot temperature, you don't have to think about maintaining that temperature. You're assuming that temperature is maintained externally. So like if you say, oh, it's 500 degrees Kelvin, it has to be spontaneous at, then it must take energy to keep it at 500. No, you're assuming that's part of the environment. That so you don't have to worry about maintaining that temperature. That's just part of the conditions. Now the equation you need to know, and I believe this is given to your data packet as well, is delta G is equal to delta H minus T delta S. And that's where the delta H, delta S, and temperature come into play. And remember, our goal is to have delta G be less than 0. So be negative essentially. Now, qualitatively, you can predict whether a reaction will be spontaneous or not based on just knowing the signs of delta H and delta S. Okay. And that's what I want to show first. Okay. So you have really 4 possibilities for what a reaction can be. It could be positive delta H, negative delta H, positive delta H, and negative delta H, and can be minus T times negative delta S, negative T times positive delta S, negative T times negative delta S. Oh, sorry, positive delta S. Can't do it alternating the same, or then I get the same answers. And then negative T times negative delta S. Those are really your only 4 combinations. Okay. And some of these are absolute, meaning that no matter what the values, size of them are, no matter what the temperature is, the sign of delta G will always be the same. Okay. Which of these scenarios, 1, 2, 3, and 4, would be an example of an absolute one where it doesn't matter what temperature is, you're always going to get the same sign? Which one of these?
Is temperature in Kelvin or
Temperature is in Kelvin. So what does that tell you, Alejandro?
It has to be greater than or equal to 0, so it's always going to be negative.
Yeah, so T is always greater than 0, so it's always going to be minus T, correct. So which one of these is absolute? Which one of these the sign of delta G never change?
Is it the second one down?
Okay. Why the second one down,
Because it'll always be negative.
Okay. Correct. This will always be, wait, hold a second. Yes, this will always be negative. So yes, sorry, brain fart. This will always be negative. So this will always be spontaneous. So always spontaneous because it will always be negative. So a negative delta H and a positive delta S always means that it'll be negative delta G, because there's no way that it can be positive, because delta S is positive and T, like Alejandro said, is always going to be positive. So it's gonna be a negative minus a value. So it's always negative. Okay. Is there another one that's always the same sign?
The very top one.
The very top one, right? Because you're doing positive minus a negative, which is a positive. So this will be never spontaneous because it will always be positive delta G because there's no way the numbers can make it the opposite. What are these last two dependent on then?
How big delta H and delta S are in relation to each other.
Let's assume that delta H and delta S are constant. So there's only one variable you can change here on. What's the variable you can actually change? So what variable can you actually manipulate in this reaction?
Temperature.
Temperature. Because the delta H and delta S of a reaction are fixed. Like if you have a certain reaction, it's always delta H and delta S, H and S will always be the same. So the only thing that you have to factor is temperature. That's the only thing that you can manipulate in this reaction. Okay. So in the first scenario, where you have positive delta H and positive S, when would this scenario be negative delta G? What kind of temperature would you want to get a negative delta G? What kind of temperature would you want? Just generally speaking, not a specific number, but just generally speaking, what kind of temperature would you want so that you would ensure yourself of a negative delta G?
Wouldn't you want like a really high temperature?
Yes, you want a really high temperature. So, because a high temperature, like you said, Katya, would raise up the negative side to make it larger than the positive side. And vice versa, you would want a low temperature here because here, temperature is hurting you because temperature is making that side more positive. So you'd want a low temperature. Okay. This is one of those examples of minimizing what you have to memorize. I don't want you to memorize this table. There's just really no need to memorize this table. I wrote it out here so you could see it and kind of logic it out, but there's no need to memorize all this because you're given this equation. And as long as you know this equation, you can plug in signs of whatever delta H and whatever delta S you want and figure it out on the fly. And it's not going to take you so much time. It's not going to take you any more time than trying to recall all this information from 21 topics of information. So I really suggest that you don't try to memorize all these four scenarios, but just think about it and logic it out and go, well, if delta H is negative and delta S is positive, well, then that's a negative minus a positive. That's always negative. Or if delta H is negative and delta S is negative, well, that's a negative minus a negative. So then if my temperature is too high, then that might overcome my delta H. So thinking things like that minimizes what you have to memorize. So figure this stuff out on the fly instead of having to memorize 12 pieces of information, because you have to memorize the sine of delta H, sine of delta S, and then the sine of delta G as well. That's just unnecessary. And I know some people might have shown you like some trick to remember like which one is which using like a grid on axes and stuff like that. Again, I'm really anti that kind of stuff because if you mix up one of your values, you're screwed. You have no idea of what you're gonna whether you're right or wrong. You're just taking on blind faith that your memory is correct, and that's not something I would risk. Okay. One second, let me just double check something really quickly. So in ideally a spontaneous reaction, you would ideally want an exothermic reaction and an increase in an entropy. Those are the two ideas that you want for a spontaneous reaction. Obviously, if you're the opposite of both those, then you'll never have a spontaneous reaction. And if you have one that favors and one that doesn't, then it depends on temperature about whether it can help you or hurt you in this scenario. Okay. Questions about that concept? Again, minimize what you have to memorize. In the calculation aspect of it, delta G is equal to delta H minus T delta S. And the key thing that you want to be aware of here is that in this scenario, delta G is kilojoules per mole, or kilojoules. Delta H is in kilojoules. Temperature is in Kelvin. But S is in joules per mole per Kelvin usually. So again, paying attention to units is really important here. And the IB is going to make sure that you are paying attention to units and aren't just blindly putting in values in here. Okay. And so the key thing here is that since these are both kilojoules, generally what you do is you divide this value by 1,000 to get it in kilojoules per mole Kelvin before you solve it. And again, this is one of those scenarios that if you write the units down, you're more likely to catch your mistake than when you don't write numbers down. Because a lot of times when you write numbers down, you just assume that they all work together. And they don't in this case, because joules versus kilojoules. And if I'm the IB, I give you in a data packet, S is in joules and delta H is in kilojoules. So really to test to see the kids that are paying attention to those units and aren't just blindly, okay, delta H minus T delta S, plug in all the values, crank out a number. Really, do you understand what you're doing and why the units are the way they are? And that's how they catch a lot of students. Units. I feel like I would be willing to probably say that when it comes to mistakes that students make, when they know the material, I feel like units are like 75% of the mistakes students make when they know the material. Like I would say the other 25%, maybe sometimes they just mix up a sign in their head, mental math or something like that. But I would say most of the times kids make mistakes on math, or most of the times kids make mistakes on conceptual stuff that has to do with somewhat math is all units, because they've done so many problems in a certain way. So they assume that it's always that way. And the IB changes it up just enough so that you can't do it that way. And then since you don't understand what you're doing, you do it the way you've always done it and assume that it's going to work. And then that's how they differentiate whether you actually understand what you're doing versus someone that's just memorized a process. Okay. Another delta G equation is negative RT ln K, which has to do with position of the equilibrium. Remember, K is the equilibrium constant. Okay. And so, but R is 8.31 joules per mole Kelvin. So therefore, in this scenario, delta G ends up being in joules per mole instead of kilojoules per mole. So again, paying attention to units and making sure that you get the units right for the question that the IB is asking. Oftentimes, the IB will state which units they want the answer in, which means that, for example, if the IB asks you to write the answer in kilojoules per mole, and you write the answer even with the right units of joules per mole, you lose a mark because you weren't following instructions there. So writing a unit at the end of the number doesn't necessarily save you from that mistake. If they say the unit in the problem that they want it in, usually in parentheses, the number that you get is all they care about. They don't care what unit you put after it. The number which you get is correct. Well, actually, I guess maybe if you put the wrong unit, they would count it wrong. But you're not required to write a unit if the unit's already explained in the question. Now, if they don't say unit in the question, then yes, you could write it in either kilojoules or joules, but your unit would have to be there for you to get the mark. So it is really important that you're aware of that. Okay. And again, though, remember, you want K to be greater than 1 so that your delta G is less than 0. Because you want ln K to be a positive number. So that way, when you do negative RT, because R and T are both positive numbers, you want a negative delta G. Okay. Questions about that? Okay. That's essentially higher level in a nutshell in about 50 minutes. Okay. We didn't get to do a lot of practice problems and things like that, but you have sources to do practice problems. And if you find some practice problems and you have a trouble with the question, feel free to kind of contact me and ask me about it. Yeah, that's essentially all the concepts that you need to be familiar with for topic 15, the energy cycles and entropy and spontaneity.